All right, example 5 is an absolute classic integration by parts example. It is routinely the problem that trips people up. It's a problem that I get asked questions about all the time. So let's go ahead and take a look at this problem. This method, I'm sure, goes by different names. There's no official name that I'm aware of. I just generally call this the indirect method. Some people call it around the corner, whatever, doesn't matter. But this is a really great example because it illustrates a way of solving a problem that is sort of implicit or indirect. And that's exactly what we're gonna see how that works here. So let's just begin naively and say, okay, we've got two different functions, an exponential and a trig. They're multiplied together, so immediately that should be red flashing lights for us as a reminder. Hey, you should think to use integration by parts. So if we use integration by parts, and if we're very strictly following LIATE, that acronym, well, because we have an exponential function and a trig function, this would tell us to choose u equal cosine of x, because t is higher than e. So u is higher up in the list, dv is lower in the list. So let's go ahead and just make it really, just boilerplate. We are following LIATE to a t, okay? Which is what somebody would do if they really were approaching this problem and they had no idea. So let's go ahead and do it that way. So we'll choose u to be cosine of x, and dv, I should say, is e to the x dx. So du is negative sine of x, and v is going to be e to the x. Okay, so I just realized I didn't put my dx here, so let's go ahead and make a little room, put my dx there. There we go, that makes me feel better. Okay, so this integral here, e to the x cosine of x dx, would become, via integration by parts, u times v, so e to the x cosine of x minus the integral of v du. Du is negative sine of x, so we get this double negative, so I'll change that minus to a plus the integral, and then I'll write my sine of x dx there. Okay. Now notice that the integral that results is essentially the same as the integral that we started with. Sure, we swap a cosine for a sine, but really, how different is sine and cosine? Effectively, to me, this integral here is literally the same thing as this integral here. Okay? And then if we're following sort of along naively or blindly, the past few examples we've done, such as examples 3 and 4 above here, they were successive applications of integration by parts. So we needed to do it twice. So some of you may very well just be happy to go ahead and say, okay, that was round 1. Round 2, let's try it again. We've got a trig function and an exponential. So we'll let our trig function, sine of x, be u, and we'll let our dv be our exponential. So then du equals cosine of x dx, and v equals e to the x. So some of you may have no problem just jumping right into another round of integration by parts. However, some of you may very well have a little apprehension or something along those lines about this particular problem. And that is because you may notice that this is just going to happen again. If we do another round of integration by parts, then this is just going to bring us right back to it's going to bring us right back to here. We're going to have an e to the x cosine of x. And for some of you, that might just be enough to make you say you're stuck and that you don't know what to do. It's going to land right back to where we started. This is going to be an infinite loop, and there's nothing that we can do. And it is true that if you keep doing integration by parts, you are going to just flip-flop integrals of the form e to the x sine of x and e to the x cosine of x. That is true. But there is a way to break out of the loop. And this is where this is a really important characteristic in a good problem solver, is sometimes, even if it doesn't seem like it's going to work out, just keep going. You don't have to waste your entire time, but there's a really good usefulness. It's a good trait to have as a problem solver, to just push the envelope a little bit. Even if you're not sure if it's going to work, even if you have some doubts, just keep going a little bit longer. Push that extra little bit. So let's go ahead, and even though we think it's not going to work, let's just go ahead and perform this second round of integration by parts. So this would become, I don't need brackets here because the coefficient is just +1, but I'm going to put the brackets here so you can see the integration by parts taking place. So this would be u times v, so sine of x times e to the x. I always like to put my e to the x's in front for some reason, minus the integral of v du. Now, like I said, these brackets here actually aren't necessary because our coefficient was just +1. I'm in the habit of doing that, but I also do think it's nice because you can see this integral becomes what's within these brackets. So it's really nice for scaffolding and seeing things in a row. But I'll just delete them now because they are unnecessary. So what we have here, effectively, is an equation. We have the equation, this integral is equal to, sure, it's equal to this integral, but it's also equal to this integral. And that's the thing. When you do a derivation in math, if you start with something, and then you have all these steps where you do something, each line, there's a reason why there are equal signs in the middle here, all the way up and down. It's because every single one of these lines is equal to all the others. You're just simplifying or doing something from one line to the next. So the very beginning, with what you started with, is equal to not only this first line, or this second line, this third line, or this fourth line. We can also say that lines 1 and 3 are equal, or lines 1 and 4 are equal to one another. So we're allowed to compare any of these. In particular, what we want to do is notice that this first integral, with what we started, is of course equal to what we have so far. Now, generally speaking, I don't rewrite this here because for me, when I view a long line of equations, I already know that, and I already know that this is equal to this, and that's how I read it. Okay? But for the sake of solving problems and getting used to it, I'm going to rewrite it there just to emphasize that really this is equal to this. Well, what we have here now is we've got this integral term on the left and this integral term on the right. Notice, if I sort of think of this as its own independent equation, so sort of, let's just put this dividing line here in the middle just to break up our thought process. Imagine that you were given this right here, and you were asked to solve for this integral. Well, you could just add this integral to each side. Just add the integral. On the right-hand side, we have -1 and +1, so they'll sum to 0. And then on this right-hand side, we'll have two copies of this integral. And then what's left over on the right are these two terms. Now, the only thing that we haven't done here that we should do is put a plus c. So that actually is how we solve for it. Well, there's one little thing I didn't do yet. two little things, I guess. I should divide by 2. So I'm not quite done yet. Let's divide by 2. And I'll also factor this e to the x out. So this would be 1/2 e to the x times sine of x plus cosine of x plus c. That's the final answer. So it's interesting because we never really actually, let me rephrase this. It feels as if we cheated, like we didn't actually do the integral, right? Because integration by parts is a way of swapping or changing up the integral. You're trading one bad integral for hopefully a improved or easier integral. Well, it's like we traded twice, landed right back with this same ugly integral, but because there was the sign difference here, because this sign difference, we were able to add it to the other side and actually solve for it. So it kind of feels like we cheated, but we really didn't, because integration by parts in and of itself does involve integration. We did integrate from here to here and from here to here. So this is a really slick method. It's kind of weird if you've never seen it before, but it's a really common thing. And it's a problem that routinely shows up because it's a classic example of an interesting application of integration by parts, and it does commonly get forgotten. So make sure you do understand this example and you can reproduce it on your own, because you are 100% guaranteed to see this problem on one of your exams or something.